This video is going to outline a simple example of the application of Hess's law using alternative enthalpy changes of reaction data. So, what do these kind of questions look like? Well, first of all, you'll be given a reaction and you'll be asked to calculate the enthalpy change of that reaction. And to do so, you'll be provided with some enthalpy change of reaction data for other reactions. Now, because Hess's law requires finding alternative pathways for a chemical reaction, you'll notice that my original reactants A and B can be found in one of the provided reactions, reaction 1. And you'll also notice that the products 2C and D are in the second reaction provided. Our job will be to use reaction 1 and reaction 2 to find an alternative pathway to get from the reactants to the products in my main equation. To do so, we might sometimes have to use a reverse reaction of reaction 1 or reaction 2. And also, we may need to multiply reactions 1 or 2 so that I end up using up or producing the right number of reactants or products. So let's consider the process in this example. Given that the reactants in my main equation are identical to the reactants in reaction 1, it's going to be a sensible place to start there. So let's write down that reaction and also the enthalpy change that we're provided with. So reaction 1 has allowed me to produce E and F. And if I look carefully at the two reactions I'm provided with, I can see E and F are also the products of reaction 2. So if I've produced E and F from reaction 1, then perhaps I can use it up by doing the reverse reaction of reaction 2. And that also helps me by producing the products that I'm looking for in my main equation. So let's write down reaction 2, but backwards, and then recognise that because I'm doing the reverse reaction for reaction 2, the enthalpy change is going to need the sign change. So the minus 15 for the enthalpy change of reaction 2 is going to become positive 15. Looking at my two equations now, and adding everything together on the left of the arrows and the right of the arrows, you'll notice that E and F are identical on both sides. So, just like in maths, you can cancel those out. There goes E, there goes F, and then write down the overall reaction we are left with, something like this. And you'll notice that the equation I've produced is exactly the same as the main equation we were asked to investigate in the first place. So how did we get to that point? Well, we added together the two enthalpy changes shown in the process section, which would be 10 plus 15, giving me a final answer of plus 25. We've ignored the units for simplicity here, but most likely they will be kilojoules per mole. According to Hess's law, this alternative route must be exactly the same as the direct route when calculating enthalpy changes. Let's now summarise the key points from this video. The first step is recognising that we need to find an alternative pathway using the reactions that I'm provided with the enthalpy change data. In more complicated examples, you may need to use reverse reactions, in which case you'll need to flip the sign on the enthalpy value, and you may also be required to use multiples of a reaction, in which case you'll need to multiply the enthalpy change value accordingly. To calculate the final value, you'll then simply need to add together the reactions you've used, and specifically you're adding together the enthalpy change values for them. Hopefully this video was of some help.